Okay, different parts of a stream from the headwaters to the mouth of the stream are going to have different processes that dominate. So up here at the top, in the headwaters, there's going to be mostly erosion. Down in the trunk of the stream, the main trunk stream, the transportation is going to dominate that system, and then at the mouth of the stream is going to be deposition. So I'm going to go through each of these parts, the headwaters and the erosion, the main trunk streams and transportation, and then we'll end way down the line at deposition at the mouth of the stream. The processes that dominate are somewhat related to the longitudinal profile. That's essentially the gradient. So at the source here, the headwaters, the gradient is going to be steep, and then as we go down towards the mouth, that gradient drops off. That gradient, along with the discharge, gives the stream its erosive power. So the headwaters is going to be steep, more erosion. The middle of the stream, the main trunk of the stream, there's going to be just movement of sediment. And then at the mouth, where gradient drops off, then is going to be deposition. Okay, in this example here, this is the front range of the Colorado Rockies, and then those streams come down, and then eventually they're going to make their way to the east. So steep, and then some trunk streams, and then deposition down here at the mouth of the stream. Okay, let's go up to the headwaters. This is an image of Linville Falls, very close to campus here at ASU. Lots of water coming over Linville Falls sometimes when we have heavy rains. Erosion is going to dominate this system. The stream flow is doing the work. The stream's energy comes from gravity, right? So it's waterfalls after waterfalls cascading water down the stream. Just like the image, that's a flood stage for the Linville River. There's going to be a large volume of water, high velocity, and erosion is going to be dominating that system. So there's a steep gradient. There's a relatively low discharge. If we think of the whole of a stream, the headwaters are up here at the top where the watershed is the smallest. So we have this broad watershed that's collecting all this water, but we're just getting the tippy top of the watershed at the headwaters. So the discharge is relatively low, but the gradient is really high. The sediment is coarse, so it's big pieces of sediment, boulders. The channel is going to be narrow and make like a V shape, where down here the water's flowing and the cross section from A to A prime across it is going to be pretty steep. And there's not going to be much of a floodplain. Like this image here of the Linville River, there's really no floodplain there. There are places around Boone where you certainly get a floodplain, like the valley of Valley Crucis along the Watauga River. So erosion is dominating. We're scouring. That running water is going to scour sediment and entrain it into the flow. There's going to be breaking and lifting of bedrock, and chunks can break off the bottom of the channel and be moved downstream. Maybe not too far, but each time there's an increase in water and a flooding event, the sediment moves a little further downstream. This is where we will also get areas like those potholes. So it's as if this hole was sandblasted, an abrasive process as the water swirls in that hole at high water, swirls around these edges, and we get these interesting shapes in the stream channel. There also can be dissolution where water is acting as a solvent and eating away at the rock. All right, so there are different ways that the channel gets bigger. If we start here with a block diagram with a stream in it, If the rocks are kind of all the same hardness as in this block diagram on the left, there may just be down cutting into a canyon, like a slot canyon here on the left. When we get to the bottom here, there's a weaker layer, maybe that spreads out the energy, and so you have a slot canyon with like a wider base to it. That would happen here on the left. On the right is what we have more of in this area, where the down cutting is in softer rocks, and so you have a lot of breaking off and slumping of the rocks, so we have more of a wider valley than a slot canyon like you might see in these more resistant to erosion rocks. Okay, in here is an image of the Grand Canyon. It has a little bit of both, right? So as it's eroding through some pretty hard sandstones, you would have a vertical cliff, and then through some shaly units, softer units, you would have more of an erosive slope. So you have steep cliffs, erosive slopes, steep cliffs, erosive slopes. They give us that real distinct shape of like a out west canyon. All right, now we've moved to the trunk stream. I have a lot of slides about moving sediment. So now we've come out of the steep area of the headwaters. Now we've got a stream now. It's got a floodplain around it. These headwater streams, I'm going to move my head here, are going to form into, the headwater streams all kind of come together to form into bigger rivers. So these big rivers, this would be, if we get to the biggest, we're talking the Mississippi around these parts, but we're talking about getting to the big streams, the New River. Transportation is the main process. We're moving fine-grained sediments down through the river system. The gradient is now less steep. The discharge it's high, but not, the highest. The sediment is no longer going to be big boulders. There's going to be coarse to fine-grained sediment, so sands to silts to muds. The valley, instead of having like in the A to A prime where it was steep, we're going to not have the stream channels edges so steep, and the gradient of the stream is not going to be so steep. And you'll be able to really define, you draw it on a piece of paper, where's the floodplain of these, the trunk stream area. This is where we're going to be moving these sediments. So on the stream channel floor, instead of having bedrock like in the headwaters, we're looking at having sand, a sandy bottom or a muddy bottom. And that's going to allow for dunes, little tiny ripples on the seafloor. So we have saltation. Remember, they're bouncing along. They're going to bounce along and then form a ripple or a little dune, and another one as they move downstream. And the way they move is the little grains bounce up the backside of the dune and then cascade down the front. So it bounces up the backside, it cascades down the front. Woo, woo. So you can watch this tank experiment to see that in action. In this middle of the stream processes, we're going to have different kinds of channels. And one kind of channel is a meandering channel here on the right, where we have meanders, point bars, and cut banks. And on the left here is a braided stream. So two main kinds of channels. And we'll look at each of those. Here's a meandering stream. Sure, we'll take a minute and watch this little video.
Compared to the whitewater streams that tumble down mountainsides, the meandering rivers of the plains may seem tame and lazy. But mountain streams are corralled by the steep walled valleys they carve. Their courses are literally set in stone. Out on the open plains, those stony walls give way to soft soil, allowing rivers to shift their banks and set their own ever-changing courses to the sea. Courses that almost never run straight. At least not for long, because all it takes to turn a straight stretch of river into a bendy one is a little disturbance and a lot of time. And in nature, there's plenty of both. Say, for example, that a muskrat burrows herself a den in one bank of a stream. Her tunnels make for a cozy home, but they also weaken the bank, which eventually begins to crumble and slump into the stream. Water rushes into the newly formed hollow, sweeping away loose dirt and making the hollow even hollower, which lets the water rush a little faster and sweep away a little more dirt, and so on and so on. As more of the stream's flow is diverted into the deepening hole on one bank and away from the other side of the channel, the flow there weakens and slows. And since slow-moving water can't carry the sand-sized particles that fast-moving water can, the dirt drops to the bottom and builds up to make the water there even shallower and slower, and then keeps accumulating until it becomes new land on the inside bank. Meanwhile, the fast-moving water near the outside bank sweeps out of the curve with enough momentum to carry it across the channel and slam it into the other side, where it starts to carve another curve, and then another, and then another, and then another. The wider the stream, the longer it takes the slingshotting current to reach the other side, and the greater the downstream distance to the next curve. In fact, measurements of meandering streams all over the world reveal a strikingly regular pattern. The length of one S-shaped meander tends to be about 6 times the width of the channel. So little tiny meandering streams tend to look just like miniature versions of their bigger relatives. As long as nothing gets in the way of a river's meandering, its curves will continue to grow curvier and curvier until they loop around and bumble into themselves. When that happens, the river's channel follows the straighter path downhill, leaving behind a crescent-shaped remnant called an oxbow lake.
Or a billabong.
O un lago en herradura.
Ou un bras mort.
We have lots of names for these lakes, since they can occur pretty much anywhere liquid flows, or used to. Which brings up an interesting question. What do the Martians call them?
Why do rivers curve? There we go. So we can see why a river might start curving. Time 1, the velocity of the river is projected to the other side of the stream. There's erosion, then it bounces over to the other side, erosion. Over time then there's a cut bank where there's erosion is going to progress. And on the inside of the meander there will be point bars. Over time that's going to get more and more pronounced. Now we have a big meander neck, and then that cutoff is going to occur usually during a flooding event, and there'll be an oxbow lake kind of left high and dry out here on the floodplain. Oxbow lakes are really important parts of the ecosystem because they become wetlands over time. And we'll talk more about wetlands. Okay, that was really awesome. They grow towards the cut banks, right? All right. These are images of those different features of a meandering stream. Here's the cut bank. It's the steep outside bend. A steep bank on the outside bend. There's active erosion that's happening. On the inside of the bend is the point bar where the water slows down. The velocity is no longer able to carry those big grain sizes, and it gets deposited. It comes out of suspension. All right, here are oxbow lakes from like a satellite image. So these swoopy lakes out here are the lakes that are now turning into wetlands, and then the point bars are leaving these scars on the landscape as well. You can see those deposits that have not yet really vegetated over. Yep, most of that I already said. Okay, levees. So there are 2 kinds of levees. There's man-made levees, like what we have along the Mississippi River to trap floodwater in the channel. There's also levees that are built by floodwaters. So here in this block diagram is before the flood, and then there's going to be a flood. So during the flood, water leaves the channel and is carrying all this brown, that sediment, out of the channel. As the floodwaters recede, then the levee is going to build up because the water receded and left the sediments behind. So here's the stream channel. It's going to grow and grow and grow with the levees on either side of the channel and become like ridges that parallel the stream channel after many floods. So they are natural levees. Also left behind from that flooding is the rich, nutrient, organic rich soils of the floodplain. All right, so that was the meandering streams. Now these are braided streams. Some of the most majestic landscapes in the world are those that are glaciated regions, and coming out of those glaciated regions is lots of sediment, and the rivers moving that sediment then are kind of choked with sediment, and those are braided streams. There's a high gradient and a fast flow. There's lots of coarse-grained sediment, so it's not really mud. It's kind of gravels and maybe some finer grain, but a lot of gravel are in braided streams. So these would be areas, like I said, active glaciation, which generating a lot of sediment, but also could be areas where rapidly uplifting terrain occurs. So if mountains are being built, then they're also being eroded at the same time, producing lots of sediment. So braided streams can be along very tectonically active mountains. Okay. So we've gone through the headwaters where there's erosion, the main trunk stream, and now we're down here at the mouth where there is erosion, transportation, and now deposition. So here we are. The water has slowed down. We're at the end of the river valley. The floodplain is very broad, very well developed floodplain at this area. The velocities flow. The water is going to get to 0. Because of that, the competency is going to get really low. Competency, remember, is the size of the sediment. So now we're barely moving mud. Deposition then is going to occur with the heavy particles. We're going to follow the suspension first, followed by the smaller grain sizes. That may give us areas where we have graded beds, so coarse grain fining up into like mud, so a fining upward sequence, and this would look like when it lithified. Deposition can occur into water, like at the ocean, but also could be at what's called an alluvial fan. These are fan-shaped aprons of sediment where a stream has come out of the mountains and hit like a valley floor, and the velocity of that stream goes to 0, and the sediment spreads out in a fan shape. These are often found in the desert. They're in the Appalachian Mountains, but there's so much vegetation, they're hard to see. Deltas. So deltas are like alluvial fan is a terrestrial deposit. A delta would be underwater. And so the delta forms, here's one from the Nile in Africa. Here is another river in Africa coming down to the Atlantic Ocean. And what's going to happen is the trunk stream is going to split into distributaries. So these little distributaries are going to bring sediment branching away from the trunk stream. So the channel may have a natural levee, and there'll be these lobes of sediment that come off of it and maybe build out into the water. All right, the Mississippi Delta is this one here, and it's what's called a river-dominated bird's foot delta. So here is the EF. Where's F? A, B, C, D, E, F. Oh yeah, F is the Atchafalaya River. So F is 4,000 BP before present. And so that's the Atchafalaya Delta, and then the Mississippi Delta is over here at E. The Atchafalaya River is actually trying to steal the water of the Mississippi River. If it weren't for the Army Corps of Engineers, the Mississippi River wouldn't flow through New Orleans anymore, because the Atchafalaya is trying to steal away that Mississippi River water. It's just always trying to find the shorter, steeper path to the Gulf of Mexico. The Mississippi Delta is shrinking. If you read about the Mississippi Delta, it's a environment. Louisiana is losing acres and acres a year of land. It's all turning into sea. Part of that is because of compaction and dewatering. So the sediments are out there, and they're getting compacted and dewatered over time. There's also decay of the organic matter in the really lush forest environments there. But then a human-induced part is that there's lack of sediment nourishing the bayou there. And what happens is the Mississippi River is so controlled that it's really not allowed to flood. So the delta becomes starved of sediment, and the river is so leveed that it projects sediment out to sea versus letting it spread out into the delta. So eventually these abandoned delta lobes here that are the wetland environment of the lower Mississippi Delta are disappearing. Okay, so it's a problem for cities that are built in these deltas. New Orleans is an example of this as well. So lack of flooding is starving the delta, and so it's along with sea level rise is causing areas like New Orleans to flood. The last bit here with the mouth of the river is this term base level, and it's kind of the hypothetical level to which the river is eroding. So in time one, here's a classic stream profile where the steep gradient in the mountains leads to this middle trunk stream, and then the delta here at the bottom as it dumps into, say, the ocean or a big lake. If we were to change base level, that is, change the level to which that stream is eroding to, it's going to look like this. So time 2, a change in base level, and this caused by faulting changes the profile. So now there's no longer that classical gradient down to the stream. It's now punctuated by an area of changing gradient here. So there's an old base level, and now there's a new base level with a lake here. So now that stream is going to erode and deposit into that lake, because the lake is like a temporary base level. Over time, that lake is going to fill up with sediment, and then the original stream profile will be achieved. So it's like an equilibrium that happens over time.